Hello and welcome to General Astronomy Lecture 9, The Origin of the Solar System. We'll begin this lecture with a pretty good question. What did our solar system look like before the planets were fully formed? The answer may lie in these remarkable images from the Hubble Space Telescope, the two on the left. Each image shows an immense disk of gas and dust surrounding a young star. Astronomers strongly suspect in its infancy our own sun was surrounded by a similar disk from which the planets of our solar system eventually coalesced. As we'll discuss in this lecture, careful study of the major features of our solar system has enabled scientists to put together a detailed theory of how Earth and our solar system was born. The theory of solar system formation is important not only because it helps us understand our cosmic origins, but also because it holds the key to understanding the nature of the planets. And again, I threw in this image here on the right. You saw this image in my very first lecture. I talked about how interesting this was and how it looks, how it is a region in which planets are forming. So you're going to learn about how that actually happens today in this lecture. So, the small sizes of the terrestrial planets compared to the Jovian planets suggests that the same chemical elements are quite common in our solar system, while others are quite rare. The tremendous masses of the Jovian planets, such as Jupiter, which has the mass of all of the other planets combined, means that the elements of which they are made, primarily hydrogen and helium, are very abundant. The Sun, too, is made almost entirely of hydrogen and helium. Its average density is 1,400 kilograms per meter cubed, in the same range as the densities of the Jovian planets. Hydrogen, which is the most abundant element, makes up nearly 3/4 of the combined mass of the Sun and the planets. So you can see that in this graphic here on the right. Helium is the second most abundant element. Together, hydrogen and helium account for roughly 98% of all of the mass and material in our solar system. All of the other chemical elements are relatively rare, and combined they make up about 2%. The dominance of hydrogen and helium is not merely a characteristic of our local part of the universe. By analyzing the spectra of stars and galaxies, astronomers have found essentially the same pattern of chemical abundances out to the farthest distance attainable by most powerful telescopes. Hence, the vast majority of the atoms in the universe are hydrogen and helium. The elements that make up the bulk of Earth, mostly iron, oxygen, and silicon, are relatively rare in the universe as a whole, as are the elements for which the living organisms are made out of things like carbon, oxygen, nitrogen, phosphorus, and other things. A wealth of evidence has led astronomers to conclude that the universe began roughly 13.7 billion years ago, with a violent event called the Big Bang. Only the lightest elements, that is hydrogen and helium, with small amounts of lithium and maybe beryllium, emerged from the enormously high temperatures that followed the cosmic event of the Big Bang. All the heavier elements were later manufactured by stars, either by thermonuclear fusion reactions deep in their interiors, or by the violent explosions that mark the end of massive stars. Were it not for these processes that take place only in stars, there would be no heavy elements in the universe, no planets like our Earth, and no humans to contemplate the nature of the cosmos. Because our solar system contains heavy elements, it must be that at least some of its material once was inside of other stars. But how did this material become available to help build our solar system? The answer is that near the ends of their lives, stars cast much of their matter back out into space. For most stars, this process is comparatively gentle, in which a star's outer layers is gradually expelled. This ejected material appears as the cloudy region or nebulosity, where nubes comes from the Latin root word cloud, that surrounds the star as it is illuminated by it, which you can see in the image here on the right. The star, Antares in this image, is shedding material from its outer layers, forming a thin cloud around the star. We can see the cloud because some of the ejected material has condensed into tiny grains of dust that reflect the starlight's light. That reflect the star's light. So dust particles in the air around you reflect the light in the same way, which is why you can see them within a shaft of sunlight in a darkened room. Antares lies some 600 light years away from Earth in the constellation Scorpio, just for reference. A few stars eject matter in a much more dramatic way at the very ends of their lives. This is a spectacular detonation known as a supernova, which will completely blow apart the star. So we did discuss supernovas briefly in my first lecture, and here we're just bringing them up again to let you know that this is where some of the elements will come from, is these explosions. They enrich the universe with their heavy elements. So these are just 3 images of supernova remnants, so what was left over after a relatively recent supernova explosion. Well, no matter how it escapes, the ejected material contains heavy elements that were dredged up from the star's interior where they formed. This material becomes part of the interstellar medium, a tenuous collection of gas and dust that pervades the space between the stars. So, as different stars die, they increasingly enrich the interstellar medium with heavy elements. Observations show that new stars form as condensations of the interstellar medium. Unlike the previous figure, which depicts an old star that is ejecting material into space, this image here on the right shows young stars in the constellation Orion that have only recently formed from a cloud of gas and dust. The bluish, wispy appearance of the clouds is caused by starlight reflecting off of the interstellar dust grains within the cloud. The grains are made of heavy elements produced by earlier generations of stars. Thus, these new stars have an adequate supply of heavy elements from which to develop a star system of planets, satellites, comets, and asteroids. Our own solar system must have formed from enriched material in just this way. Thus, our solar system contains recycled material that was produced long ago inside a now dead star. This recycled material includes all of the carbon in your body, all of the oxygen that you breathe, and all of the iron and silicon in the soil beneath your feet. So that is why I have this quote here: "The cosmos is within us, we are made of star stuff, and we are a way for the universe to know itself." We are that recycled material. We are literally made out of material from dead stars. So it's really a beautiful thing. And you'll hear me bring this up a lot because it's a prevalent theme throughout the course. All right, well, stars create different heavy elements in different amounts. For example, oxygen, as well as carbon, silicon, and iron, is readily produced in the interiors of massive stars. However, gold, as well as silver, platinum, and uranium, is created only under special circumstances. Consequently, gold is rare in our solar system and in the universe as a whole, while oxygen is relatively abundant, although still much less abundant than hydrogen and helium. So this graph is just showing you that. So you can see the relative abundances, so this shows you how much there is in the universe. So it gives you an idea. In fact, we mentioned specifically that gold is very rare. I just recently saw a quote, I don't know how accurate it is, but I do believe it. I was surprised, though, that all of the gold that's ever been excavated from the Earth is only enough to fill up 3 Olympic-sized swimming pools. So that gives you an idea of how rare it is, and that, you know, why it's a pretty expensive item. It's because there's only 3 full swimming pools of it out there. Anyway, so these small cosmic abundances of elements other than hydrogen and helium help to explain why the terrestrial planets are so small. Because the heavier elements required to make these terrestrial planets are rare, only relatively small planets can form out of them. By contrast, however, hydrogen and helium are so abundant that it was possible for these elements to form the larger Jovian planets. So, from the abundances, so you can reference the previous slide, do you expect that water, which is H2O, might be a common substance in the galaxy? Take a minute to reference the image, pause your video, and return when ready. Well, the answer in this case is a resounding yes. It turns out that hydrogen, which is one of the main components of water, it is the first most abundant element, and oxygen, the other component of water, is the third most abundant element. So with that train of thought, if it's the first and third most common element in the universe, well, it's not unreasonable to think that water would be quite common. So it actually is. Water is common throughout the universe, it's just often frozen because it is so cold. The heavy elements can tell us even more about the solar system. They help us determine its age. The particular heavy elements that provide us with this information are radioactive. A radioactive nucleus therefore ejects particles until it becomes stable. In doing so, a nucleus may change from one element to another. Physicists refer to this as radioactive decay. All right, so we're going to get into some slightly technical stuff. I'll skip over all of the really tougher stuff and just give you kind of a general idea. If you'd like, you can look this up a bit more for more detail, but a lot of it is external to this introductory course. So just know that there are some heavy elements that we consider to be radioactive, and that means that they will eject particles from their nucleus until they become stable and turn into something else. So that is the process in very quick, vague terms of radioactive decay. So for example, a radioactive form of the element rubidium, it has the atomic number 37 on the periodic table, it decays into the element strontium when one of the neutrons is decayed into a proton and an electron. So again, these might be terms that you're not too familiar with if you haven't taken many science courses yet, but the idea is that one element may turn into another because of this decay. The first step in understanding how we learned the age of our solar system is to understand exactly what we mean by the age of a rock. A rock is a collection of a great many atoms held together in solid form. The atoms must be older than Earth, having been forged in the Big Bang or in stars that lived long ago. Right? So the elements that make up our rocks are older than our planet itself, because they had to come together and then form our planet. We cannot determine the ages of the individual atoms because old atoms are indistinguishable from new ones. However, some atoms undergo changes with time that allow us to determine how long they have been held in place within a rock's solid structure. In other words, the age of a rock is the time since its atoms became locked together in their present arrangement, which in most cases means the time since the rock last solidified. Experiments show that each type of radioactive nucleus decays at its own characteristic rate, which can be measured in the laboratory. Furthermore, the older a solid rock is, the less of its original radioactive nucleus remains. This behavior is the key to a technique called radioactive dating, which is used to determine how many years ago a rock cooled and solidified, or simply to determine the ages of rocks. For example, if a rock contained a certain amount of radioactive rubidium when it first solidified, over time, more and more of the atoms of rubidium within the rock will decay into strontium. The ratio of the number of strontium atoms that the rock contains to the number of rubidium atoms gives a measure of how old the rock actually is. And this image here, this graph, shows you another example of that. When the rock first formed, it might have been entirely potassium and no argon. But over time, potassium will decay into argon. So over time, we can see the relative amount of each isotope. So knowing the exact amount of the rock by taking some samples, you can compare it to what we know, and you can figure out the exact age of that rock. So it's a very useful technique, and this is how we date things on the Earth. This is how we know the age of our Earth and of our solar system. Speaking of that, this radiometric or radioactive dating tells us how long it has been since a rock solidified, which is not the same as the age of a planet as a whole. For example, we find rocks of many different ages on Earth. Some rocks are quite young because they formed recently from molten lava, and others are much older. The oldest Earth rocks are about 4 billion years old, and some small mineral grains date to almost 4.4 billion years ago. But even these are not as old as the Earth itself, because Earth's entire surface had been reshaped throughout time. Moon rocks brought back by the Apollo astronauts have also been dated, and many are older than the oldest Earth rocks, demonstrating that parts of the moon's surface have not changed since the very beginnings of its history. The oldest moon rocks come back to be about 4.5 billion years old. To go all the way back to the origin of the solar system, we must find rocks that have not melted or vaporized since they first condensed out of the interstellar medium. Meteorites that have fallen to Earth are a source of such rocks. Many meteorites appear to have remained unchanged since they condensed and accreted in the early solar system. Careful analysis of radioactive isotopes in these meteorites show that the oldest ones formed about 4.54 billion years ago. So this must mark the beginning of our solar system. We have seen how processes in the Big Bang and within ancient stars produced the raw ingredients of the solar system. But given these ingredients, how did they combine to make the sun and the planets? So that's what we're left at now. That is our question. Astronomers have developed a variety of models for the origin of the solar system. The test of these models is whether they explain the properties of the present-day system of sun and planets. The central idea of this model dates back to the 1700s, when the German philosopher Immanuel Kant and the French scientist Pierre-Simon de Laplace turned their attention to the manner in which the planets orbited the sun. Both concluded that the arrangement of the orbits, all in the same direction and in nearly the same plane, could not be a mere coincidence. The nebular theory begins with the idea that our solar system was born from the gravitational collapse of an interstellar cloud of gas called the solar nebula that collapsed under its own gravity. The solar nebula probably began as a large, roughly spherical cloud. I lost my train of thought. A roughly spherical cloud of very cold and very low density gas. Initially, this gas was probably so spread out, perhaps over a region of a few light years in diameter, that gravity alone may not have been strong enough to pull it together and start its collapse. Instead, the collapse may have been triggered by a cataclysmic event such as the impact of a shock wave from the explosion of a nearby star. So we start out with this big collection of gas and dust, and we think that it would collapse when something triggers it. We don't think gravity alone would do it. Something must have triggered it. That's the current theory. Once the collapse started, gravity enabled it to continue. Remember that the strength of gravity follows an inverse square law with distance. The mass of the cloud remained the same as it shrank, so the strength of gravity increased as the diameter of the cloud decreased. Because gravity pulls inward in all directions, you might at first guess that the solar nebula would have remained spherical as it shrank. Indeed, the idea that gravity pulls in all directions explains why the sun and the planets are spherical. However, we must also consider other physical laws that apply to a collapsing gas cloud in order to understand how orderly motions arose in our solar system. So at this point we know we had some collection of gas and dust out there called the solar nebula. Each part of it had some gravitational attraction to the next part, but it wasn't enough to drive collapse of the entire cloud. So a shock wave is what we believe would trigger that. And once the shock wave triggers some collapse, then gravity allows that to continue. And then from there, we start to see it rotating and flattening into a disk. All right. So as it contracted, the greatest concentration of matter occurred at the center of the nebula, forming a relatively dense region called the protosun. As its name suggests, this part of the solar nebula eventually developed into the sun. The planets formed from the much sparser material in the outer regions of the solar nebula. Indeed, the mass of all the planets together is only 0.1% of the sun's mass. When you drop a ball, the gravitational attraction of Earth makes the ball fall faster as it falls. So it's that same idea here. Once it starts collapsing toward the protosun, it starts moving faster and faster. So in the same way, material falling inward toward the protosun would have gained speed as it approached the center. As this fast-moving material ran into the protosun, the energy of the collision was converted into thermal energy, causing temperatures deep inside the solar nebula to rise. This process, in which the gravitational energy of a contracting cloud of gas is converted into thermal energy, is what we call Kelvin-Helmholtz contraction, after the 19th century physicists who first described it. As the newly created protosun continues to contract and become more dense, its temperature continued to climb as well. After about 100,000 years, the protosun's surface temperature stabilized at about 6,000 degrees Kelvin. But the temperature in its interior kept increasing to ever higher values as the central regions of the protosun became more and more dense. Eventually, after perhaps 10 million years had passed since the solar nebula first began to contract, the gas at the center of the protosun reached a density of about 10 to the 5 kilograms per meter cubed, which is about 13 times more dense than typical iron, and a temperature of roughly a few million degrees Kelvin. Under these extreme conditions, nuclear reactions that convert hydrogen into helium began in the protosun's interior. These nuclear reactions released energy that significantly increased the pressure in the protosun's core. When pressure built up enough, it stopped that contraction of the protosun, and thus a star was born. In fact, the onset of nuclear reactions defines the end of the protostar stage and the beginning of a star. Nuclear reactions continue to the present day in the interior of the Sun and are the source of all of the energy that the Sun radiates into space. So, in very brief terms, basically what happens is as this ball of gas contracts, it starts to heat up, and it heats up enough for fusion to occur. And that's how we get our Sun at the center. If the solar nebula had been rotating at all, everything would have fallen directly... if it had not been rotating at all, everything would have fallen directly onto the protosun, leaving nothing behind to form the planets. Instead, the solar nebula must have had an overall slight rotation, which caused its evolution to follow a different path. As the slowly rotating nebula collapsed inward, it would naturally have tended to rotate faster. We're getting into a little bit of physics here, but this relationship between the size of an object and its rotation speed is an example of the general principle called conservation of angular momentum. Figure skaters make use of this conservation of angular momentum. When a spinning skater pulls her arms and legs in close to her body, like you can see on the right, the rate at which she spins automatically increases. In the same way, the solar nebula spun more and more rapidly as its material contracted toward the center. Astronomers see young stars that may be forming planets today in the same way that our solar system did billions of years ago. As the solar nebula began to rotate more rapidly, it also tended to flatten out. But why? So again, this is a little bit of physics here, but from the perspective of a particle rotating along with the nebula, it felt as though there was a force pushing the particle away from the nebula's axis of rotation. This is kind of like how passengers on a merry-go-round or spinning carnival ride seem to feel a force pushing them outward and away from the center of the ride. This apparent force was directed opposite to the inward pull of gravity. So gravity is pulling in, and they feel this apparent force outward. And so it tended to slow down the contraction of material toward the nebula's center. But there was no such effect opposing contraction in a direction parallel to the rotational axis. So basically what this is saying is that after 100,000 years of its first formation, when it first started to contract, it had developed a structure with a rotating and flattened disk surrounding what would have become the protosun. So you've got gravity pulling in, but you also have a force pulling some material out. So it takes that material and just stretches it and basically flattens this ball into a disk. So this disk is what we call a protoplanetary disk, since planets form from its material. This model explains why their orbits all lie in essentially the same plane and why they all orbit in the same direction. Just think of a big spinning disk. All parts of the disk spin in the same direction and in the same plane. So here is a visual overview of the entire process, starting from the top left and working down to the right. So quick summary, you start out with a giant ball of gas and dust. A shock wave probably triggers its collapse, and as that happens, gravity can help continue that collapse. As it collapses, it has some general overall spin, so as it starts to condense, that spinning speeds up. It becomes more rapid because of that conservation of angular momentum, just like a figure skater. But as it starts to spin a lot, it starts to flatten out because of that stretching effect that we mentioned. So you start to get a disk, and then from that disk, we begin to form some planets. Now, again, I show you that image here that I showed you in the first lecture because you can see its similarity now to what we've been talking about. So this was theory, and this is new observational proof. Notice how similar they are. Well, we actually have more direct visual proof of these objects. So the Orion Nebula, which you see on the left, is a star-forming region located about 1,500 light years from Earth. The smaller bluish nebula above it, the smaller bluish nebula is the object shown on the right. The four insets are false color close-ups of four protoplanetary disks that lie within the nebula. A young, recently formed star is at the center of each disk. The disk at the upper right is seen edge on, and the one in the lower left shows it in comparison to our own solar system. So these are visual proofs of protoplanetary disks. So we know these do occur. This is direct evidence. So what we'll do, what we've done so far is discuss how we go from just random material in space to a star system, but we haven't really talked about how this material now forms the planets. So that will be our next lecture, Lecture 10. Thanks for watching, and have a great day.